right, so how many of you have read the lab? How many of you have had a chance to look at the video from last year at all? Okay. All right, so what is the point of this lab? So it kind of seems like a counter, but it turns out that it's not going to be much of a counter when we do the state diagram. It is a counter because, you know, it has a sequence and has to follow that sequence. When we do the state diagram, it's not going to be like it doesn't seem much like it's counting. You're not doing any logic to make it like increase a number of any sort. Now, I had this, okay, so what I have here, and hopefully it will show up, is the basis board, and it is programmed with the lab from last semester. So you should be able to see it using my phone camera to show it. So actually it does not look like it is currently programmed, so I need to send it the program. So where is Veda? There it is. Bitstream generation failed. That's not good. We hate that. Yeah, y'all have seen that. Let's see. Probably I changed some things right before. Let me just change them back. So I was playing around with some new constraints. What's that? Oh, yeah. Well, if they worked, they're a lot easier. But as of yet, it does not work. So I will start this compiling. As y'all have already discovered, sometimes it takes a while to compile. And then it can take a long time to compile, and then just at the last minute, it'll tell you, oops, just kidding. We get an error. Are y'all familiar with, have y'all figured this part, this right here to comment and uncomment? If you have like blocks of things that you want to comment out or uncomment. All right, so the idea in this particular lab is that you are going to program the basis board to count in a certain sequence that you are told in the lab handout. And it's going to display that sequence on the 7-segment display, 1, 2, 3, 4, 5, 7-segment display on the basis board. And so there's two things that you're going to be learning. One is using a state diagram for setting up this counter, and continuing to practice programming finite state machines. And then the other one is learning how to use the 7-segment display. Have y'all used the 7-segment display before? You have. Okay, so tell me how it works.
So there's 4 different segments, and each of them are like A and something.
Okay, so 4 different displays. Okay.
And then each display has 2 sections. It's like
Huh?
Like the,
Uh-huh.
and then they can get even further with like specifically which, like the A, the B, the F, etc.
Yep. Okay. So, and so we'll do that part second after we talk about the first part, which is really going to be the easiest part, which is setting up the state diagram, because the state diagram is going to be pretty simple. And so if you're just trying to get the pre-lab done, that's going to be easy. So let's look at what the lab says to do. It says, so you have all of this information about the 7-segment display, which we're going to go over, and then also talks about the case statement, which we are going to talk about. And then it says for the pre-lab, you will design and build a synchronous 3-bit counter with an enable input, so the enable and clock signals are the only inputs. Now the clock signal is not going to be the clock, it's going to be a button on the board that you will use to advance the clock. And it is to loop through the following sequence: 7504136, 7504136. So that's 7. Okay, and the output count is to be displayed on one of the 7-segment displays of the Basis 3 board. If you're looking at the video from first semester, spring semester, that in the spring semester they had to have the display go from like one display to the next, to the next, to the next, and then back around. So they had to change which display is on. Y'all do not. And so you don't need to do that part. You can pick the display that you want to use and use that for the entire time. So I'm going to choose a different sequence, just so that I'm not actually doing your lab for you, which, sorry about that, but let's have it just go in the sequence 1, 3, 5, 7, 9, 0, 3, 4, 5, 6, 2. So we're going to have it go in that sequence. Now, I'm going to recommend that when you go about assigning numbers to these, I did start recording, yeah. Assigning numbers to these, that you assign them in order, and you'll see why. So, like, it might be tempting to say, well, let me just call the state that has 1, the binary number 1, and the state that has 3, the binary number 3. But it'll be a lot easier if you call them 0, 0, 0, 0, 0, 1, 0, 0, or 0, 1, 0, if you have them go in order, and you'll see what I mean by that. Okay, so what does our finite state machine do? What's that? Yeah, it just loops through the count sequence. Does it always do that?
Yes.
Let's take a look at the instructions. It says a synchronous 3-bit counter with an enable input, so the enable and the clock signals are the only inputs. What is an enable input? Yeah, so if it's not enabled, it's not going to do anything. So, and so it does not always count, only if the enable is enabled. So, so the clock we're not going to worry about. We're just going to assume that it goes to the next state on the next clock cycle, but only if enable is equal to 1. So if we're at the reset and enable equals 1, we're going to go to our first state, which will be, I'll call it state 1. I'll call it 1, and I'll call it A. Okay, now what if enable equals 0? We'll just go back to reset. And is this going to be a mealy or more type machine?
More.
Hmm?
Oh, actually,
Wait,
Well, so we don't really count the clock as an input because the clock is always going to be on the next clock cycle. Uh, does it? It does kind of depend on the enable input. So in that sense, yes. If we put the enable aside, then it only depends on the state that it's in, and so um, in that sense, it's more. So, uh, so it's kind of a combination of those because, and so I'm just going to say if it's in a particular state, it's going to display the number that's on here. So I'm going to say my output is the number that's on there. So that's actually going to be my output. It's actually going to be a binary string that we're going to send to the 7-segment display. Okay, so now if enable equals 0, we're just going to go back to where we were. And then if enable equals 1, then we're going to go to the next state where our output is 3. And I'll call that state B. That's supposed to be a 3. Yours will be different. It'll be whatever your count sequence is. And then from here, if enable is 0, it'll just stay where it is. And then if enable is 1, it'll go to the next one, and so forth through all 7 states. 1, 2, 3, 4, 5, 6, 7, and then back to the starting one. So A, B, C, D, E, F, G, and then back to A. And then each time your output will be whatever the binary string is that corresponds to the display that you want to have. Sorry, my handwriting is so bad. And then at each state, if it's not enabled, it just stays where it is. So each of these has an enable equals 0, just looping back to it. And I'll come back to this in a second. I want to see if if it compiled this time. It did compile this time. Okay, so I will show you all how this works.
What are you saying, like, under the letter?
I'm saying output equals.
Okay.
And it is very easy to unplug this thing, and as soon as I unplug it, it loses the program, and then I'll have to send the program again. Okay, so here's the basis board. this one, it currently is saying 0. I don't know what it would have said if I hadn't had the enable switch. I'm going to turn the enable switch off, and so right now it's not enabled. I have set that, I think this bottom button right here, that's the one that I think I have set as the clock. We'll see in a minute. But right now, since enable is not set, it's not doing anything. But when I turn the enable switch on, so enable turned on, and now, so last time I did this, we had it advance through the different displays and had a different count sequence, but you can see that that's what it's doing with a little bit of glare there. So that is the basic idea of what is supposed to happen, except it's supposed to be just on a single display. Okay, so now let's go back and figure out what our state table should look like. So this is pretty much one of the easiest ones that you're going to do. How many states do we have?
7.
Are you sure?
Oh, 8.
8. So we have to have a 3-bit counter. So do we need to use all 3 bits?
No, I can use 2.
Well, well, there's 7. Okay, even if we just had 7, we'd still need to use 3, because for to 2 we'd only have the max we could have is 4. Do we have too many to use 3 bits? Not really, kinda, sorta, but not really. So we can get all 8 in there. So 8 will do. So we'll have our current state. And we'll have our next state. And we'll have our output. And we'll have our next state, and we'll have 2 possibilities, enable equals 0 and enable equals 1. Did I call reset A or did I call 1A? Okay, did I give reset a letter?
No.
Okay. Okay, so enable equals 0, that is, our next state is easy. It's going to be exactly the same. So when enable equals 0, it'll be exactly the same. If you were designing this from scratch and not using Vivado or Verilog, how many flip-flops would you need? 3. And if enable equals 1, on the next clock cycle, it should just advance to the next state. And your output is going to have, you're actually going to have 2 outputs. You're going to have your output that is going to be your AN string, and you're going to have an output that's going to be your the lab calls it C, and that's usually what it uses for the 7-segment display. I call it seg, and the reason I call it seg is for laziness, because that is what it's already called in the constraints file, in the constraints template, and so when I use that, I don't have to rename it. So that's why I call it that. Now, we don't know yet what these are going to be because we haven't talked about them yet, but these are going to be binary numbers, and AN is going to be a 4-bit binary number, and the segment is going to be a 7-bit binary number. So now we're ready to talk about what those are going to be. So now we'll go back to that. Any questions on doing the state diagram? Okay. So we'll come back to this and fill it in. Okay, so now we're going to remind ourselves of how the 7-segment display works. You have to give it 2 signals. You have to tell it which display, and you have to tell it which ones of the LEDs you want to have lit up. And it is an active load control, so that means whichever one is 0, that's on, and 1 means off. And notice that the order, so the order is important. So when we define our AN, we can define it as being either 0 to 3, or we can define it as being 3 to 0. And either one is fine. You just have to keep track of which bit you're calling 0. So if I have AN 0 to 3 equals 4B 0101, so if I'm using that, and that's what I say AN is, if I'm using 0 to 3, then what that means is AN 0 is 0, AN 1, it shouldn't be, I need to have just 1 0, sorry. So 4B 1011. So AN 0 is 1, AN 1 is 0, AN 2 is 1, and AN 3 is 1. So when I have it written 0 to 3, then having the 0 right here tells me that AN1 is the one that is selected. So this tells me that I'm using display 1. But if I use this, if I define my vector like this, then, and I use the same exact number, 4B1011, then in this case, AN3 equals 1, AN2 equals 0, AN1 equals 1, and AN0 equals 1. So in this case, display 2 is selected. And what happens a lot of times is, I know with me, is I think I have it straight in my head as to which way I'm doing it, and then I run my program, and I'm pretty sure everything's good, except whatever shows up on the display just doesn't look like a number. It just looks like hieroglyphics or something. Usually means that I had it backwards as to which one it was going to be, because this is how we're going to set up our segment, or C. So I prefer to do it from 0 to 6. The reason why is as follows. In the template, the constraints template, The order that it's in, so W7, seg 0, W6, seg 1, in the order that it has it right here, the way that it's set up matches the way I think about the 7-segment display, which is as follows. I think about it as starting here and going down and going around and then going up and then coming here. So this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6. And so when I think of it that way, and I think of, well, how would I encode a 3? Then in my head, I think I start at 0, and I want that one. So I would define my seg equals 7b. So I'm writing what the string would be for the, is that a 3? That's a 3. Starting 7, so it's a 7-bit binary number. I start at the top. I want that one, so I'll make that 0. And then I want the next one, so I make it 0. I want the next one, so I make it 0. I want the next one, I make it 0. I don't want the next two, so I'll make them 1. And I want the next one, so I'll make it 0. And so it's just the way I think about it. So the way I think about it is I start, you know, in my head, I'm so used to thinking of my 7-segment display as having these. And so I start at the top and then I work my way around, and then that way I don't have to think too hard about what my segments are going to be. But to write it that way, I would need to start with 0. So that's how I do it, and that ends up being how 90% of 27 of Digital Logic 2 students do it, because they watch my video, and that's how it ends up getting done. So, but you don't have to. You can define them either way. So whenever you want to display something on the 7-segment display, you're going to send it both an AN and a segment. So you will have to have. Did I post the constraints template, or do y'all know where the constraints template is?
It's a mobile.
Okay, so the things that you will have to use for this lab. You don't have much. You will have to have a switch, and I believe you get to choose whichever switch you want. I think I was lazy and I just chose the first one in the list, which makes it the one all the way over on the right. You will need to have your 7-segment display, and I was particularly lazy and just called it seg, so that way all I had to do was uncomment from the constraints file. And then if you call this AN instead of A, you don't even have to rename these, because in the template file it's AN and not A, but I called it A, so you'll need to have that. And so those are the only ones you'll need to have on your constraints. So before we talk about doing the programming part, are there any questions so far? Yes?
I got most of them said it, but in vector, what's the 0 stand for?
Yeah. So when I declare this vector A, I'm going to declare it either from 0 to 3 or from 3 to 0, and those are just corresponding to, it's like an array in computer science, and so the 0 corresponds to, so when we think of a number, we usually think of it like in this order. And so 0 being the least significant bit, and 1 next, and then 2, and then 3. So when I write A, 3:0. What I mean is that this is 4 bits, so 3210, and the last bit in my number is the 0th bit, and then that's what it means. Did that answer your question? Okay.
Thank you.
All right. So let's talk about our general strategy for how we're going to program it. So,
I have one last question.
yeah.
Can you scroll up a little bit? You said how you said you were trying, like how you would, like for example, make a sig for that weird E looking thing.
Uh-huh.
I can tell like it's like 0, 1, 2, 3, but how did you make that to that sig?
Okay, so I wanted the number 3,
Yeah.
which if I'm using these, that's how to get it.
Yeah.
So that is the ones that I have shaded in here are positions 0, 1, 2, 3, and 6. So of my 7 segments, this is, I defined it as starting with 0, 1, 2, 3, 4, 5, 6. So this is backwards from how we normally do it, but that's just because that's how I do it.
Okay.
And so every place where I wanted it to be lit up, that has a 0. And so I put a 0 for 0, 1, 2, 3, and 6. And the ones that are not lit up, I put a 1.
Okay, I understand that. Thank you.
Yeah, okay? And so, and you're gonna have to do these for all of the numbers. You'll have to figure out what they are for all the numbers. Yes?
Yeah, I think you also might have said this, but so it's active low, not just for the selection, but also for the segments, right?
I did not say that, but yes, it is. So thank you for mentioning that. It's active low for not just the select, but also the segments as well. Yep. Okay, so we're going to talk about our big picture of how our program is going to work. So big picture, we're going to have module, and then you'll call it whatever you want to call it. This is Lab 8. And you'll have your inputs and your outputs. Our only inputs are enable and clock. And our outputs are AN and seg. I call it seg because I'm lazy. Your lab handout calls it C. It's not that big a deal to go through and change seg to C, so whatever you want to do. So input will be EN and clock. Oh, I forgot that one. You have the additional, in the constraints, you also have the clock, and that is important to do it right. Your clock needs to be done like this. You have this in one of your labs gives you, I think it's in the constraints file too. I think it's like the very first thing in the constraints. And so all you'll do with this is whatever button you want to use for your clock, you just put that here. You can also use a switch if you want to use a switch instead of a button. A switch can sometimes be handy because a button can sometimes like false fire, and a switch might be a little better. Okay, and then we're gonna our output, but our outputs are gonna be reg, and why are they gonna be reg? Because they appear inside of an always block. So you're gonna have output reg. Yes.
Does our A, like our selection, need to even like be in an always block? Since in our case we only selected 1, couldn't we technically just take it out the always block and let it be forever?
You absolutely could. Yep. So you don't, if you wanted to, you do not have to have this be in the always block. So you could make this output like that, and then instead of having assigning it inside the always block, you could just have at the very beginning, assign A equals 4B1110, or whichever display you chose. And now my program's going to give me errors for all the other places where I give a value, but you could certainly do that, and that would be quicker. I just didn't, going back to the lazy thing, I already had this written from last semester, so didn't rewrite it. But yeah, so that would be, if you're doing this the first time, that would definitely be a way to do it, and so I'm taking these out. Now I use, force a habit, tend to use non-blocking assignments inside my always block, but it doesn't really matter in this case because it's not like it's something you're gonna like accidentally be writing over something that you would need. Okay, so I have also, in addition to our inputs and outputs, so in addition to our inputs and outputs, now I did my output low Indian with the 0 to 3 just to match it with my seg, but then it doesn't match with my queue and next queue. So yeah, however you want to do it is fine. Now, what do you think that queue and next queue are? What do you think I have? What do you think I'm doing with those?
Not clock count, count.
Yeah, so that's the output. That's telling us what state we're in. And so the way that I suggested that you always do your finite state machines is that you always are going to have 2 blocks. You're always going to have, so then I also had here reg, queue, and next queue. And those were 4 bits. Do we need 4 bits or just 3 bits? We just need 3 bits, right? Yeah. Yeah, so 2 to 0. Now, the reason I would say to make these 2 to 0 is because I think we want to do these as actual binary numbers because I think that will be most useful. So what do I mean by that? Let's go back to our state table and let's assign these binary numbers 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And look how nice that is. We're using all of them, so we don't even have to worry about, I mean, when I use a case statement, I always like to have a default in there anyway, but since we're actually using all of them, you wouldn't have to have a default. And I'll explain about that when we get to what we're going to do with the case statement. Now, you don't have to define them this way, but it makes it really easy if you do define them this way, because within your always block, you're going to have a case statement, and your case statement is going to be based on whatever state you are currently in. So I have it at always at enable and queue. So whenever enable changes or Q changes, it's going to figure out what the next state is going to be. Q is the current state. You don't have to call it Q. You can call it current state. You can call it number. You can call it LED. You can call it whatever you want. So case Q says based on whatever Q is, then you're going to tell it what to do. Now, you might want to define parameters. We had done parameters before. Do y'all remember how to do parameters? So I have this set up that where I have, depending on what Q is, if Q is the binary number 0, 0, 0, we're going to do this. If Q is the binary number 0, 0, 1, we're going to do this. But we could also do it with parameters. What's the syntax for this? I can't remember syntax for any languages because it's like they're all slightly different. That's all you have to do? Okay. Did not open up the right lab. So we could do parameter A equals, now I can't use A because I'm using A for something else on mine. So parameter reset equals 3 B000, comma, I'll call it AA just because I already have an A, equals 3 apostrophe B001, comma, B equals 3B010, comma, C equals 3B011, comma, D equals 3B100, E equals 3B101, F equals 3B110, and G equals 3B111. Okay, so that way, when you have those parameters, then you can, when you do your case statement, you can just say, you don't have to have the binary number here, you can just say case Q. So if I'm at reset, then when I'm at reset, what do you want the segment to be? And the segment is going to be whatever segment you want it to display. And what do you want the next state to be? And so since we put our states in order, our next state can always just be the state you're in plus 1. So if we hadn't put them in order, you would have to say our next Q is, okay, if I'm in reset, my next Q is D. Okay, and if I'm in state E, my next one is C. But since we did them in order, we can always just say the next Q is just Q plus 1. So that was just a little trick to make that happen. And as a matter of fact, could we take it out of the case statement and just do it once? I think we could. So I think it could be. I think we could have this. Any reason not to do that? I think I might want to take this enable out of here. Why would I want to take the enable out of my sensitivity list?
Want to trigger whenever the enable is switched?
Yeah, I don't want it to I don't want it to making changes when the enable is switched. I just want the enable to make it happen or not. So I'm going to take that out of there, and then once I do that, I'm going to take this. I'm going to take the next Q out, because I don't need to, that's going to be the same for all of them. So I can take that out, and I can put that just inside my always block. And then all I have to do with each state, I don't even need a begin and end now, because I only have one thing for each case. So for each case, all you have to do is tell it what segment you want to display for that case. So, so for reset, I'll display whatever I've got there. Now mine, why I have mine as a 7-bit instead of, wait, ours is 7, yours is 7, yeah, okay, never mind. I usually do 8-bit because I usually include the decimal point. So these are just random strings. They're numbers, but I don't know what they are. These are not the correct numbers for yours, so you don't want to copy them. But you would have for each one of these. So notice what I'm saying is, before, because I had multiple things in here, I had both the segment and the next Q, and I had the A, had multiple things. I had to have a begin and end. But now I just have one thing in each of them, so I don't have to have a begin and end. And so I can just say for each one what this next segment is going to be. And I'm just going to make stuff up. And we're going to compile it and see if it works. I think I'll put a 1 there. And this time I'll make 1, 1, and 0, 0. And like I said, force a habit, I'm using the non-blocking assignment with the little arrow and the equals, but that's not necessary here. I hope somebody just copies exactly what I do here and then wonders why their numbers are all messed up. Because that's what happens when you don't watch the whole video. That's what happens when you just zoom into the code. And what, we had A through G and a reset? Anyone have any idea why? Oh, because I had a space. Okay, and then I always like to have a default. Not necessary here because we are doing all 7, but I mean all 8. So then we shouldn't need any of the rest of this. And then you have to have an end case. I need to have a colon after my default. End case end. Okay, so now you'll have your second always block. And so your second always block is what's going to happen on the positive edge of the clock. And here's where I use the enable. So here I say if it's enable, then Q equals next Q. Otherwise, don't do anything. Just stay where you are. But we didn't need to put a stay where you are inside the first always block because that's what it'll do if we don't tell it to change. I mean, you could do that. You could have with each one of our case statements, you could have if enable, Q next state is, else next state is, just stay where you are. But that would be a lot of extra code for no reason. So let's see now. Let's see the constraints. We have that. I also made a what do you call it? A something. I'm drawing a blank. The
Simulation.
yeah, but what's the name for the kind of test bench? I also made a test bench, but doesn't seem to be. I'm not gonna worry about that today. So let's see what happens if I do open elaborated design. Yes, let's save. Background task is running. Yes.
Just kind of a random question, but I know in like a past video you said like you had like multiple always blocks that like run at the same time, but in each individual always block, does the code run one line at a time sequentially?
It depends. So that is the point of using the non-blocking assignment. So the non-blocking assignment makes it so that it's not necessarily sequential, but if you use equal signs, then the equal signs it will.
And like if you have like an if statement up here, it's gonna check that first before it does that.
Yes, yeah,
Thank you.
it does do that. But what you have to be careful about, and especially when you start thinking about your project and how your project is going to work, is you really want to a lot of times like assign something inside an always block under one condition, but then under another condition assign it somewhere else, and you're just not allowed to do that. So it's like whenever you if you have something that is a reg, then it needs to be assigned in one always block and one always block only. Now you will always get this warning message whenever you use the clock. Huh, that's not what I was expecting.
It worked.
Well, we don't know if it worked yet. Oh, I see a problem. Does anyone else see my problem?
The A03.
Like, I'm defining A one way here and another way here. But I don't know where I did that. Or how. Oh, did I?
Did you set something equal to A with one A instead of A with two A?
Oh, that's what I did. That is what I did. Yep. That's it. Thank you. That was it. That was it. So because I'm going to be brave and say that was surely that was the only mistake, and I'll go to generate bit stream. Let's see what happens. Okay, so while it is busy finding the other errors that I didn't think of, are there some questions? You feel like you know what to do?
Do like if you like have like well I guess at first, what is the benefit of having multiple always blocks?
Okay, so that's an excellent question, and every semester people ask it. And so it's not just the benefit of having it, but when you have a finite state machine, when you're using flip-flops, it's really important. The whole point of a flip-flop is that it changes just on the clock edge. So you want the change to only happen just on the clock edge. But when the clock edge happens, you need it to be ready to go right then. You need to have everything all calculated. So you have the one always block that does all of the calculations and gets everything all ready to go. It says, okay, as soon as that clock hits, this is the change that's going to happen. And then the other always block is just for the clock. Just for the clock, and then every once in a while you stick another thing in there like the enable. Because remember how we said when we first started this, we said, is it mealy, is it more? And I said, well, it kind of sort of depends on the enable. And then we threw that enable in there in the second always block. And so if it had really depended on the enable, then like if the enable like had some effect sometimes and other effect other times, it would have shown up in the first always block, and we would have had an if statement, like if enable, do this, and if not, do that. I think I just rambled for a minute because I don't really think I was answering your question at that instant.
Right, I think
Okay.
that was my big point.
Yeah, and it is important, and a lot of times what happens, especially people who are good programmers, try a different design when they start because they're like, I got this, I don't, she doesn't know what she's talking about, I can do this myself, and they'll try it, and you might be able to come up with something that works, with one machine or that works with another one, but this kind of basic setup is a good setup for all of your finite state machines. Still no error, so yes. So what would happen if it's not enabled?
Q just maintain. Q doesn't get changed.
Yeah, Q doesn't get changed. Yeah. And so inside your first always block, oh, I didn't set next Q. It doesn't work. It doesn't work. Okay, so I do have to have a begin and end. And, oh wait, no, we did. We did. Yeah, we did. Because, okay, right, because we took it out of each, yeah, we took it out of the case statement and we did the next Q up here. That's right, because we said it was the same no matter what. That's right. Okay. Usually, in almost every other design that you're going to do using state diagrams, you're going to set the next state within these cases. It is very rare that you're going to say, you just blanket next Q is going to be Q plus 1, but that's because we're counting in order. Even though our count sequence is not really in order, we tricked it to make it count in order by defining our numbers this way. Getting real close, running. I have no idea why it takes so long to compile. I mean, this is 2024. This is.
Is there any way in Prelab to like print stuff out in the console without using a test bench?
Without using a test bench.
Like if I ever want to just like, I'm tweaking over a problem and I just want to like print to help debug or something, can I just not do that?
I think you can. It's writing the bit stream right now, so as soon as it does that, we're going to run it, and then I'll check that, and that'll be an outside of regular. Outright bit stream complete. All right. And now, for fun, will it recognize the board? You never know. Oh, let's reload this and see what it looks like. Uh-oh. Okay, I'm just pretend I don't see that. And then what usually happens is at this point, I'll start pressing the button and nothing will happen, and I'll be like, oh no, why doesn't it work? Okay, so I assigned it to this button, and I pressed the button, and oh no, nothing's happening. Why is nothing happening? Yeah, I need to make sure I have that, whatever switch I assigned. And now I'm counting in this invented language that I made up. Some of them, look at, some of these are real numbers. So it does in fact work. So y'all are now like officially good to go. Any last questions before I stop this? I'm going to get yours after I. Can I do what? Yeah. Which part? Okay, so here. Now note this is not actually going to work for you. You know that. Okay.
You know, it says do your code for that, but it doesn't ask for it in Prelab.
Yeah, now depending on who you have oh wait, y'all are digital logic too, so never mind. Oh, yeah. All right, so Zoom people.